A faint rhythmic pulse echoes from a dead star 1,000 light-years away. That signal traveled across the cosmos, not as light or radio waves, but as a ripple in the fabric of reality itself. This is the secret language of the universe, written in gravity, and we are only just beginning to learn how to listen. By the end of this, you will understand how these cosmic ripples could rewrite the rules of space travel and communication forever. We will explore how a ghostly particle, the Graviton, might hold the key to crossing impossible distances. We will uncover why our galaxy might be buzzing with conversations we are too primitive to hear. What do you believe is waiting for us in the silent dark between the stars? That rhythmic pulse from a dead star is a whisper in the fabric of spacetime, but what carries the message? To answer that, we must shrink down to the smallest possible scale, to the realm of quantum mechanics. Here, the force of gravity is not a curve in spacetime as Einstein described. Instead, it is believed to be carried by a ghostly messenger particle, the Graviton. Think of it like this: you know how light is made of tiny packets of energy called photons. A photon is the particle that carries the electromagnetic force. In the same way, a graviton would be the particle that carries the force of gravity. It is the theoretical exchange particle, the tiny courier that would communicate the gravitational pull between two objects. This creates a fundamental clash in our understanding of the universe. Einstein's general relativity paints gravity as the elegant warping of spacetime, like a heavy ball sitting on a stretched rubber sheet. The graviton, however, suggests that this warping is actually the result of an endless, invisible shower of these particles being exchanged between all things that have mass. So why have we never found one? The problem is one of incredible weakness. Gravity is the feeblest of the fundamental forces by a staggering margin. The gravitational pull between you and this screen is so unimaginably weak that detecting the individual particle responsible for it is beyond our current technology. A single graviton signal will be drowned out by the background noise of the universe. It is like trying to hear a single raindrop fall in the middle of a roaring hurricane. This is why the graviton remains one of the greatest unsolved puzzles in all of physics. We see its supposed work everywhere, from apples falling to planets orbiting, yet the worker itself remains forever hidden in the shadows. So if the graviton is the ghostly messenger, then gravitational waves are its shout. For decades, this was pure theory, an elegant prediction of Einstein's equations that seemed too faint to ever catch. Then, in 2015, everything changed. A pair of facilities known as LIGO, the Laser Interferometer Gravitational Wave Observatory, heard it. They detected a tiny, fleeting wobble in the fabric of spacetime itself. The source was a cosmic catastrophe that happened over 1 billion years ago, the final death spiral of two enormous black holes. As these monstrous objects spun around each other at nearly the speed of light, they churned the very fabric of the universe, sending out ripples that traveled for eons before finally reaching us. This was not a gentle wave, it was a violent storm in space-time, a literal shaking of reality. Think of the quiet surface of a still pond. Now imagine dropping two incredibly dense stones, watching them orbit each other faster and faster until they splash together and vanish. The ripples that spread out are gravitational waves. They are not made of matter or light. They are pure geometry, stretches and squeezes of space itself. When they passed through the Earth, they made the entire planet expand and contract by an almost impossibly small amount, a fraction of the width of a single proton. That LIGO could measure this is one of the most astonishing technical achievements in human history. Since then, we have heard other cosmic crashes, including the collision of two neutron stars. These events are so powerful they forge gold and platinum, literally shaking the universe to create the elements that make up our jewelry and technology. Scientists often call these detections the sound of the cosmos. The data is even converted into audio, a low thrum that rises to a final chirp as the two objects merge. It is the sound of spacetime ringing like a bell. These waves travel at the speed of light, carrying with them a pure, unaltered story of the most violent events in the universe. They are the direct evidence of gravity in motion, a chorus of whispers and shouts from the darkest corners of reality. That ringing of spacetime is a cosmic chorus, but to understand its true nature, we must listen more closely. The gravitational waves detected by LIGO are a triumph of general relativity, a confirmation of Einstein's vision of a dynamic, warping universe. Yet this very success pushes us toward an even deeper mystery, one that lies at the frontier of all physics. How do these vast, smooth ripples connect to the frantic, probabilistic world of the quantum? This is the grand challenge, the bridge between the very large and the very small. In theory, a gravitational wave is not just a geometric ripple. It could also be thought of as a coherent stream of those ghostly gravitons, all moving in sync. Think of it like a laser beam. A laser is not just a wave of light, it is an organized march of photons, all moving together with the same energy and direction. In a similar way, a powerful gravitational wave could be envisioned as a laser-like beam of gravitons. The wave is the macroscopic reality we can measure, while the graviton is the proposed microscopic particle that would compose it. This is why unifying Einstein's beautiful geometric theory of gravity with the bizarre rules of quantum mechanics is considered the holy grail of physics. We have two incredibly successful theories that describe our universe, but they speak different languages. General relativity explains the cosmos, from the bending of starlight to the expansion of the universe. Quantum mechanics explains the atom, from the structure of matter to the forces that hold it together. But in extreme places, like the center of a black hole or the first moment of the Big Bang, both theories are needed simultaneously, and they completely disagree. Unifying them would be like finally discovering the root language from which all other dialects of reality emerged. It would give us a single, consistent set of rules that work from the smallest quark to the largest galaxy cluster. Within that unified theory, the graviton would take its rightful place alongside the photon, not as a hidden phantom, but as a fundamental character in the story of the cosmos. Until we make that connection, our understanding of the universe's deepest language remains frustratingly incomplete. This is where our story shifts from discovery to invention. We now know that spacetime can ripple, and we suspect gravitons are the cause. But what if these ripples could be shaped by intelligence? This leads us to a breathtaking idea, the concept of a graviton wave. This is not just a natural gravitational wave from a black hole collision. A graviton wave would be a gravitational wave that has been purposefully engineered, modulated to carry a message or perform a task. Imagine the difference between the random crash of thunder and the complex, information-rich sound of a human voice. Both are vibrations in the air, but one is noise, the other is language. A graviton wave would be the voice, not the thunder. The core of this idea is modulation. Our own technology is built on this principle. We take a pure, steady radio wave and then subtly alter or modulate its properties to imprint sound, data, or images onto it. This carrier wave then travels vast distances, delivering its encoded information. Now apply that to gravity. A theoretically advanced civilization could generate a stable, powerful gravitational wave. They could then modulate it, perhaps by varying its frequency or amplitude in a complex, deliberate pattern. This pattern would not be a natural product of a cosmic crash. It would be a structured code, a sequence of ones and zeros written directly into the geometry of spacetime itself. This would be a gravitational signal, a true language of the cosmos that uses the fabric of the universe as its medium. The implications are staggering. Such a signal would be almost perfectly clean, traveling across the galaxy without the distortion that plagues light and radio waves. It could punch through cosmic dust clouds and pass by stars without being scattered or absorbed. If you wanted to send a message across unimaginable distances, this would be the ultimate delivery system. But communication might only be the beginning. If you can control gravity, you are not just controlling a signal, you are controlling the very framework of distance and motion. The ability to generate and shape these waves could open a doorway to something even more profound, a way to move through space that defies our current understanding of physics. Our galaxy is unimaginably vast, and our current methods for crossing it are tragically inadequate. Every rocket we have ever built operates on a simple and brutal principle, the tyranny of the rocket equation. To go faster, you need more fuel, but that extra fuel adds more weight, which then requires even more fuel to push that extra weight. This creates a vicious cycle where the required fuel grows exponentially with every extra mile per hour you want to achieve. To reach even modest fractions of the speed of light with a crewed ship, you would need a fuel tank larger than the planet itself. It is a logistical trap from which there seems no escape. Consider the sheer distance to our nearest stellar neighbor, Proxima Centauri. It is about 4.2 light-years away. That means a beam of light, the fastest thing in the universe, takes over 4 years to make the journey. For a modern chemical rocket, that same trip would take over 70,000 years. That is not a voyage, it is a monument to futility. Even our most advanced theoretical concepts, like nuclear fusion propulsion, would struggle to cut that journey down to a human lifetime. The problem is not just speed, it is the emptiness. The space between stars is not just a void, it is a shooting gallery of radiation and micrometeoroids against which a ship traveling at relativistic speeds would be incredibly vulnerable. A collision with a speck of dust no larger than a grain of sand would release the energy of a nuclear bomb. So we are trapped not by a lack of ambition, but by the unforgiving physics of reaction mass. We are trying to swim across an ocean by pushing against the water behind us, and the ocean is simply too big. If we are ever to become an interstellar species, we cannot fight the universe with brute force. We must learn to speak its language, to use the fabric of reality itself as our engine. This is where physics meets science fiction in a theoretical blueprint for a starship. In 1994, a physicist named Miguel Alcubierre proposed a radical solution to the problem of interstellar travel, a concept now known as the Alcubierre drive. It is not an engine that pushes a ship through space. Instead, it is a device that moves space itself. The idea hinges on a direct manipulation of space-time using gravity to create a warp bubble. Imagine a surfer riding a wave. The surfer does not move through the water itself carries the surfer forward. An Alcubierre drive would work in a similar way. The ship sits inside a stable bubble of normal space-time. In front of the ship, the drive would compress space-time, pulling the destination closer. Behind the ship, it would expand space-time, pushing the point of origin further away. The bubble itself and everything inside it would then be surfing a wave of distorted geometry. Crucially, the ship inside this bubble is motionless relative to its local environment. It is not accelerating through space, so it does not experience the crushing g-forces or the complications of time dilation that come with near-light speed travel. The space around the bubble is what is moving, and according to Einstein's general relativity, nothing can locally exceed the speed of light, but space-time itself has no such speed limit. The universe expanded faster than light in its earliest moments. An Alcubierre drive would, in theory, harness that same principle for propulsion. This is where our ghostly Gravitons re-enter the story. To create this incredible warp bubble, you would need to generate and control titanic gravitational fields. You would need to shape space-time itself, bending it to your will. The only conceivable way to do this, according to our current understanding, would be by manipulating the fundamental carriers of the gravitational force. You would need a technology capable of producing a coherent, directed stream of gravitons, orchestrating them to compress spacetime ahead and expand it behind. The Alcubierre drive is not just a faster ship, it is the ultimate expression of gravitational control, a machine that speaks the secret language of spacetime to command the universe to carry it forward. While the energy requirements are currently beyond fantasy, the underlying principle offers a glimpse of a future where we do not fight the cosmos but dance with it. The elegance of the Alcubierre drive blueprint shatters against the sheer magnitude of its engineering demands. To even begin constructing such a marvel, we would first need to solve problems that currently border on magic. The first and most daunting hurdle is energy. Creating a detectable, engineered graviton wave, let alone a full warp bubble, would require power on a scale that defies human industry. Some theoretical estimates suggest you would need to harness the equivalent of Jupiter's entire mass converted directly into pure energy. Picture every star in our galaxy, and then imagine concentrating a fraction of that awesome power into a single machine. Our entire planetary energy output over the next million years would not even register as a spark against such a requirement. This is not a challenge of building a bigger power plant, it is a challenge of redefining what power means. Beyond raw energy lies an even stranger requirement, the need for something called exotic matter. This is not just a new type of material, it is a substance with a property that seems to contradict reality, negative energy density. Normal matter, everything we have ever touched or seen, gravitates. It pulls things together. Exotic matter would do the opposite. It would create a kind of gravitational repulsion, pushing spacetime apart. We have never found or created a stable form of this material, though faint quantum effects hint that it might be possible in microscopic amounts. To build a warp drive, you would not need a few atoms. You would need mountains of this impossible stuff, just to stabilize the bubble and prevent it from collapsing into a singularity. The final challenge is one of unimaginable precision. Manipulating spacetime is not like welding steel. You are not working with a physical substance, you are working with the geometry of reality. The slightest miscalculation, a tiny flaw in the gravitational field you are generating, could have catastrophic consequences. It would be like trying to perform brain surgery with a jackhammer, where a tremor of a billionth of a degree could tear the ship and the space around it into unrecognizable fragments. This is not engineering as we know it. It is a form of cosmic artistry, requiring a control over nature so complete that it looks indistinguishable from a god's. That same control over gravity could spark a revolution in how we speak to each other across the stars. Our current attempts at interstellar communication are like shouting across a crowded, noisy room with our hands over our ears. Radio waves, our primary method for listening to the cosmos, are fragile. They are easily scattered by interstellar dust, absorbed by nebulae, and drowned out by the natural radio chatter of pulsars and quasars. The signal degrades, the message is lost, but a signal carried by gravity would face none of these obstacles. Gravitational waves pass through matter as if it were not even there. A planet, a star, an entire galaxy, they are all virtually transparent to this ripple in spacetime. Imagine trying to have a conversation through a thick, dense fog with a flashlight. The light beam scatters and fades. Now, imagine you could send your voice through the ground itself as a vibration that travels cleanly through the fog, the trees, the very hills, arriving with perfect clarity on the other side. That is the fundamental difference. A modulated graviton wave would be that vibration for the cosmos. It would carry its encoded information through supernova, through dust clouds light years thick, and through the hearts of black holes completely unaffected. The message would arrive not as a faint, crackling whisper after thousands of years, but as a sharp, pristine signal, as clear as the day it was sent. This would enable more than just simple greetings. We could transmit vast libraries of data, complex schematics, or even sensory experiences across thousands of light years with no loss of fidelity. It would be the ultimate communication channel, turning the silent, isolating vastness of the galaxy into a connected network. The universe would suddenly feel much smaller, and the conversations happening within it would finally be audible. The pristine clarity of a gravitational signal presents us with a new and profound challenge. Our current ears for this cosmic language are crude and nearly deaf. The LIGO observatory is a marvel, but it is akin to a prehistoric creature feeling the tremors of a distant earthquake. To truly listen, to decode the subtle modulations of an engineered graviton wave, we would need to build an entirely new kind of ear, one sensitive enough to hear the faintest whispers of spacetime itself. The next step in this evolution is already on the drawing board, a project called LISA, the Laser Interferometer Space Antenna. Imagine taking LIGO's 2.5-mile-long arms and scaling them up to millions of miles, and then placing this entire instrument in the pristine quiet of space. LISA would consist of 3 spacecraft flying in a perfect triangular formation, with laser beams shining between them over a staggering distance of 1.5 million miles. In the vacuum of space, free from the rumbling of earthquakes and the noise of human activity, this giant triangle would be able to hear gravitational waves that are far quieter and at much lower frequencies than LIGO can perceive. It would listen to the gentle spirals of smaller black holes, the subtle hum of white dwarf binaries, and perhaps even the faint background rumble from the Big Bang. But even LISA, for all its grandeur, would still be listening to the roar of cosmic events. To hear a whisper, a deliberate signal encoded onto a graviton wave, we would need to go further still. We would need to move from detecting the wave to detecting the particle. This would require a technology that does not yet exist, a quantum gravity sensor. Think of the difference between feeling the vibration of a drum and isolating the individual air molecules that carried that vibration. A quantum sensor would attempt to do the latter for gravity. It would be an instrument so exquisitely sensitive that it could register the impact of a single graviton. The challenges are beyond immense. A graviton is so weak that its interaction with matter is almost non-existent. To detect one, you would need a detector that is perfectly isolated from every other force in the universe, cooled to near absolute zero to eliminate thermal vibrations, and shielded from every stray particle and cosmic ray. It would be like trying to hear the flap of a butterfly's wing from 1,000 miles away while standing in the middle of a hurricane. Yet, if we could build such a device, the universe would open up in a way we can barely comprehend. We would no longer just be listening for catastrophic crashes. We could tune into the gentle, constant background hum of gravitons being exchanged by every object in the cosmos. We could, in theory, point our sensor at a seemingly empty patch of sky and read the information encoded in a graviton beam, a message sent not with light or radio, but with the very fabric of reality. The data stream would not be a simple chirp, but a complex river of ones and zeros, a language waiting for its Rosetta Stone. The act of decoding that signal would be the ultimate test, forcing us to look for patterns that are not born of chaos but of a mind. What would the first sentence from the stars actually say? The profound silence of the cosmos has always been our greatest mystery. We scan the heavens with radio telescopes, listening for a whisper in the static, and find only a vast and unsettling quiet. This is the heart of the Fermi paradox. Given the sheer number of stars and planets, the universe should be teeming with life. So where is everybody? Perhaps we have been searching for the wrong thing, in the wrong way, using the wrong language. Our entire method of listening is built on the electromagnetic spectrum, on light and radio waves. But what if that is the cosmic equivalent of trying to find someone in a modern city by looking for smoke signals? A civilization that has mastered gravity would have graduated from this primitive chatter. Their ships would not blaze through the void on fiery rockets visible from light years away. They would slip through space-time itself inside warp bubbles we cannot see. Their conversations would not be broadcast in easily intercepted radio waves. They would be encoded in subtle ripples in the fabric of reality, ripples that pass straight through our planets and our detectors without a trace. To them, our frantic radio and television broadcasts might be nothing more than background noise, the faint, chaotic crackling of a species that has not yet learned to speak. We are like ants on a forest floor, unaware that just above us there is a network of highways and fiber optic cables carrying conversations we cannot perceive. The great silence is not empty. It is filled with a conversation we are too deaf to hear, written in a language we are only now learning to read. This changes the entire question. It is not where is everybody, but rather how do we learn to listen for the words already being spoken all around us. The great silence might be an illusion, a trick of our own technological limitations. While we strain to hear a deliberate signal, the cosmos could be filled with natural broadcasts so complex they blur the line between physics and language. Consider the death spiral of two neutron stars. When these incredibly dense stellar corpses finally merge, they do not just produce a simple gravitational thud. They generate a rapidly rising chirp, a precise and intricate waveform that sings a detailed story about their masses, their spins, and the very nature of matter under extreme pressure. This is not a random crash. It is a cosmic symphony with a clear beginning, a rising crescendo, and a final, defining chord. To a sensitive enough detector, this chirp is packed with information, a structured pattern emerging from chaos. Could an ancient spacefaring civilization, one that thinks in gravitational terms, listen to that chirp and recognize it not just as a natural event, but as a recognizable form of communication, a standard signal used across the galaxy? Then there is the steady, low hum. Across the universe, supermassive black hole binaries, pairs of these monsters orbiting each other at the hearts of galaxies, are predicted to generate a constant, rhythmic background of gravitational waves. This is not a brief chirp, but a perpetual drone, a bass note underlying all of creation. It would be a signal of immense stability and power, one that persists for millions of years. What if a species learned to use this constant hum as a carrier wave, a steady drumbeat against which they could broadcast more complex information, hiding their messages in plain sight within the universe's own heartbeat? And beyond known physics lies the truly mysterious, the theoretical vibrations of cosmic strings. These are hypothetical, infinitely thin defects in the fabric of space-time, relics from the universe's first moments, stretching across cosmic distances. If they exist, their vibrations would create sharp, distinct bursts of gravitational waves, like the pluck of a gargantuan violin string. The pattern of these bursts would be mathematically pure, a sequence of perfect oscillations. To any listener, such a clean, artificial-looking signal would be incredibly difficult to explain through known natural processes. It would beg the question, is this a crack in the universe or a signature? The challenge for us, then, is not just to build better ears, but to develop a new form of cosmic literacy. We must learn to distinguish not just between noise and signal, but between a random scream and a word that just happens to be spoken by a star. This strange link between gravity and the quantum world leads us to one of the most mind-bending ideas in all of physics. It is a hypothesis that suggests the universe is far more deeply connected than it appears, a concept known as the ER=EPR conjecture. At its heart, this idea attempts to solve two great mysteries at once: the nature of quantum entanglement and the fabric of space-time. Quantum entanglement is that famously strange phenomenon Albert Einstein called spooky action at a distance. It occurs when two particles become linked, their fates intertwined. Whatever happens to one particle seems to instantly affect the other, no matter how far apart they are, even if they are on opposite sides of the galaxy. This connection appears to violate the cosmic speed limit, the speed of light. But what if this spooky action is not action at all? What if it is not a signal traveling through space, but a shortcut through it? The ER equals EPR conjecture proposes that these two entangled particles are not actually separated by a vast emptiness. Instead, they are connected by an incredibly tiny, microscopic bridge in the fabric of spacetime, a wormhole. In this view, entanglement is not magic, it is geometry. The particle on your left is not sending a message to the particle on your right faster than light. It is that the two particles are, in a very real sense, right next to each other, linked by a tunnel that bypasses normal space entirely. This is where our elusive gravitons re-enter the story. If this conjecture is correct, then what is it that holds this microscopic wormhole open, that maintains the bridge between the two entangled particles? The most compelling candidate is the graviton. The endless exchange of these ghostly particles between the entangled pair could be the very glue that stabilizes the connection, that keeps the shortcut viable. The graviton would be the fundamental worker maintaining the infrastructure of this quantum link. It would be the reason why the two particles can share a single state, because they are not truly separate. They are two ends of the same cosmic thread, with gravitons constantly weaving that thread together. This idea transforms our understanding of reality. The universe might not be a collection of distant, isolated points. It could be a vast, tangled network of these microscopic bridges, a quantum web of connections where every entangled particle is a tiny stitch in the fabric of spacetime itself. The spookiness of action at a distance vanishes, replaced by a profound and intimate geometry. The force that holds planets in their orbits and the phenomenon that links particles across the void might be two sides of the very same coin, both speaking the silent language of gravity. Building a device to speak the language of gravity would be the ultimate engineering feat. Let us walk through a thought experiment, a step-by-step blueprint for a graviton transmitter using the principles we understand today. The first and most daunting challenge is generating a powerful, coherent gravitational field. We cannot simply amplify gravity the way we amplify light. We have to create it from scratch. One theoretical method involves creating a microscopic black hole. Black holes are the universe's most powerful gravitational engines, warping spacetime with unimaginable force. In a lab, we might use a colossal particle accelerator, one that circles a planet, to concentrate enough energy into a single point to create a black hole no larger than an atom. This tiny singularity would be incredibly unstable, evaporating in a fraction of a second due to Hawking radiation. To sustain it, we would need to constantly feed it with energy, a process requiring precision beyond our current comprehension. An alternative, slightly less terrifying approach might involve manipulating neutron star matter. A single sugar cube-sized piece of this material weighs as much as a mountain. By spinning a contained sphere of this ultra-dense substance at near light speed, we could, in theory, generate a controllable and powerful gravitational field. This spinning heart would become the core of our transmitter. With our gravitational engine established, the next step is shaping its output. A raw, chaotic gravitational pull is useless for communication, it is just noise. We need to mold this force into a stable, coherent wave. This is where the concept of exotic matter becomes essential. We would need to surround our gravitational core with a shell of this theoretical substance, a material with negative energy density. This exotic matter would act as a lens, focusing the gravitons being emitted by our core into a tight, directed beam, much like a laser. Without this lens, the gravitational field would simply spread out in all directions, weakening into undetectable nothingness. The precise geometry of this lens would determine the wave's frequency and amplitude. To encode a message, we would then introduce subtle fluctuations into the power feeding the core. A brief, timed dip in energy could represent a 0, while a sustained peak could represent a 1. we would be rhythmically squeezing and releasing the fabric of spacetime itself, imprinting a binary sequence directly onto the gravitational wave. Imagine tapping your finger on the surface of a still pond in a specific pattern. The ripples carry your message outward. We would be doing the same, but our finger is a microscopic black hole and our pond is the universe. The final and perhaps most delicate phase is message encoding and transmission stability. Let us choose a universal message, the mathematical constant pi. Its endless, non-repeating sequence of digits is a signature of intelligence, a pattern unlikely to occur in nature. Our device would modulate the Graviton beam to broadcast this sequence over and over. A 1-second pulse for a 1, a half-second pulse for a 0, spelling out the first few thousand digits of pi in the language of gravity. But maintaining this signal is a constant battle. The gravitational forces at play are titanic, and any instability in our containment field or our exotic matter lens would cause the entire system to collapse. The warp bubble around the transmitter would flicker and distort, scrambling the message into gibberish or, in a worst-case scenario, collapsing into a gravitational singularity that consumes the laboratory. Success would mean achieving a perfect balance, a delicate dance between unimaginable power and flawless control, allowing us to broadcast our cosmic hello into the silent fabric of the universe. That first transmission would echo through the galaxy for millions of years, a permanent testament to who we were. The choice of what to send in that initial Graviton wave is not merely a technical decision, but a philosophical one of staggering weight. Do we introduce ourselves with the cold, hard facts of our existence, or with the messy, beautiful essence of our humanity? The scientific consensus often leans toward universal constants. We could broadcast the value of pi, the prime number sequence, or the precise frequencies of a hydrogen atom. These are the building blocks of reality, a language any technologically advanced species would almost certainly recognize. It is a safe choice, a quiet nod from one mathematician to another across the void. But is safety what we want our first impression to be? Another proposal is to send a map. This would not be a map of streets and cities, but a cosmic one. We could transmit the precise positions and movements of the planets in our solar system, pinpointing Earth's location with gravitational coordinates. We could even include the unique chemical signature of our atmosphere, rich with oxygen and the telltale traces of industrial activity and life. This is a bold and generous act, an open invitation that says, here we are. Yet, it is also an act of profound vulnerability, a cosmic shout that reveals our exact address to a neighborhood we do not yet know. Then there is the code of life itself, our DNA. Sending the entire human genome would be the most intimate introduction possible. It would be like handing another civilization the complete blueprint for a human being, from our genetic strengths to our inherited vulnerabilities. It tells them what we are made of, but it says nothing of what we have built, what we dream, or what we fear. It is a biological fact stripped of all culture and context. Or we could strip everything back to a simple, heartfelt greeting, a single, repeated symbol of peace, a wave, not a weapon. This approach speaks to our hopes rather than our intellect, focusing on our desire for connection above all else. Each option carries a different vision of ourselves. Are we primarily scientists, explorers, biological specimens, or diplomats? This single message would define humanity for any listener, a snapshot of our entire species frozen in a ripple of space-time. The responsibility is almost paralyzing. That first Graviton wave would be more than a signal. It would be our legacy, a single sentence written into the fabric of the universe that says, this is who we were, and this is what we believed was most important. For decades, our primary method of scanning the heavens for company has been to listen for the crackle of radio waves or the flash of laser light. This is the grand tradition of SETI, the search for extraterrestrial intelligence, a patient and hopeful vigil in the electromagnetic spectrum. Our most powerful radio telescopes tirelessly sift through cosmic static, searching for a pattern, a signal that stands out from the natural hum of pulsars and the whisper of the Big Bang's afterglow. It is a search for a needle in a haystack the size of a galaxy, but it operates on a reasonable assumption that a developing civilization like our own would use these obvious forms of energy for communication and radar. Yet this entire approach might be fundamentally limited, like trying to find an expert sailor by scanning the horizon for a wooden raft while missing the nuclear submarine gliding silently beneath the waves. A civilization that has mastered gravity would have no need for such primitive signaling. Their communications would be far more advanced and far more difficult for us to detect. This realization is sparking a quiet revolution, the birth of a new field sometimes called gravitational SETI. The core idea is audacious: to look for signs of intelligence not in the electromagnetic chatter, but in the subtle geometry of spacetime itself. Instead of searching for a structured radio signal, we would look for a gravitational wave that does not fit the natural template. Imagine analyzing the data from LIGO or its future successors and finding a signal that is too perfect, too steady, or too complex. A gravitational wave that maintains a single, pure frequency for years, like a sustained note from a cosmic tuning fork, would be deeply suspicious. Nature does not create perfect, endless sine waves. It creates the chaotic chirps and rumbles of colliding black holes. A signal like that could only be the product of a stabilized engine, a machine designed to sing one specific note into the fabric of the universe. Or perhaps we would find a signal that is modulated with a complex mathematical sequence like pi or the prime numbers imprinted onto the wave. Finding such a pattern would be the gravitational equivalent of hearing a voice emerge from the random noise of the wind. It would be a technosignature, a clear fingerprint of technology imprinted directly onto reality. These nascent searches are the first, tentative steps in learning to read the universe's deepest language. We are no longer just listening for a shout in the radio band. We are learning to feel for a deliberate hand, gently shaping the cosmos itself. This invisible architecture of the cosmos holds a secret we have never seen. For nearly a century, we have known that galaxies spin too fast to hold themselves together. Stars on the outer edges should be flung into the void, yet something unseen holds them in place, a cosmic glue we call dark matter. It does not emit, absorb, or reflect light. It only interacts with the universe in one way, through gravity. We feel its pull, but we cannot see its face. What if this is not a limitation, but a clue? What if dark matter is not just affected by gravity, but is a substance that speaks gravity's language as its native tongue? This leads to a breathtaking hypothesis. The dark matter that forms the hidden skeleton of the cosmos might communicate with itself through graviton waves. While our visible universe chatters with light and radio, this shadow universe could be buzzing with a constant, silent conversation conducted entirely through ripples in spacetime. We are like people living on a tiny, isolated island, unaware that the vast ocean around us is filled with whales singing complex songs to one another just below the surface. Our inability to see dark matter might not be because it is inert, but because we are deaf to its primary method of interaction. This idea transforms our search for it. Instead of building larger detectors to catch a rare, direct particle collision deep underground, we might instead learn to eavesdrop on its gravitational chatter. A sufficiently advanced gravitational wave observatory, like the future LISA mission, could one day tune into the background hum of the cosmos and hear something new layered beneath the roar of black holes. It might detect a faint, structured static, a gravitational murmur that does not match any known astrophysical source. This could be the collective signal of dark matter particles interacting, a soft symphony playing in the void. The implications are staggering. Unlocking this gravitational channel would not just identify a missing component of the universe, it would open a window into an entire parallel reality that has been intertwined with our own since the beginning of time. We would be witnessing the fundamental network of a shadow cosmos, finally understanding that the great silence we perceived was merely our own ignorance of the deepest, most pervasive language of all. A starship surfing a warp bubble faces a paradox far stranger than distance. Einstein's theory of relativity introduces a relentless consequence of high-speed travel known as time dilation. For a crew traveling at a significant fraction of light speed, time itself would slow down inside the ship relative to the rest of the universe. A journey that felt like 5 years for the crew could mean 50,000 years had passed on Earth. They would return to a world that had forgotten them, a future so distant their own civilization might be dust. This is the ultimate loneliness, a separation not just by space but by time itself. A conventional rocket pushing against this relativistic barrier condemns its passengers to this fate, but a Graviton-driven warp drive proposes a radical escape clause. Remember, the ship inside an Alcubierre bubble is not moving through space, it is being carried by moving space. It is technically stationary within its own local frame of reference. This is the critical distinction. If the ship is not undergoing acceleration through space, then the severe time dilation effects of special relativity might not apply. The crew would experience time normally, a steady 1 second per second, while the bubble itself surfed the wave of distorted spacetime. The drive would not just be bending space to cross vast distances, it would be bending the rules of time to preserve the traveler's connection to their own era. This is the grand promise of gravitational control. It suggests a future where we do not just travel from point A to point B, but we travel through time and space as a unified whole, arriving at our destination not as relics from a forgotten age, but as contemporaries of the world we left behind. The very particles that govern the pull of gravity could become the guardians of our timeline. The staggering energy needed for a Graviton engine forces us to look beyond our planet, beyond our sun, and toward the very heart of cosmic power. To generate the gravitational waves required for communication or warp travel, we must first learn to command energies that dwarf all of human civilization's output. One classic vision of such power is the Dyson sphere, a megastructure that would encapsulate an entire star to harvest its total energy output. Imagine a vast swarm of solar collectors, numbering in the trillions, orbiting so close together they form a shell around a star. This network would catch every single photon of light, converting the star's immense fury into usable power. For a civilization capable of such a feat, the energy from one star might be enough to power a single, focused Graviton transmitter, turning a sun into a cosmic lighthouse whose signal is written in spacetime, not light. Yet even this might not be sufficient. For greater power, we must look to a more potent and more dangerous source, matter-antimatter annihilation. This is the ultimate conversion of mass into energy, a process 100% efficient. When a particle of matter meets its antimatter counterpart, they obliterate each other in a flash of pure energy, releasing power on a scale that makes nuclear fusion look like a campfire. A spacecraft powered by this principle would need only a small amount of fuel to achieve incredible speeds, but containing that fuel is a monumental challenge. Antimatter is the universe's most volatile substance, requiring magnetic bottles of immense precision, where a single system failure would result in an explosion that could vaporize a continent. To power a warp drive, you would not need kilograms but mountains of this explosive material, a logistical and safety nightmare of almost mythical proportions. Beyond these lies the most speculative source of all, the quantum vacuum. Empty space, according to quantum mechanics, is not truly empty. It is a seething foam of virtual particles that pop in and out of existence in a constant energetic dance. This background energy of the universe, the zero-point field, is everywhere. If we could find a way to tap into this endless sea of quantum fluctuation, to extract even a tiny fraction of its energy, we would have a power source that follows us wherever we go. A ship would not need to carry fuel, it would drink from the fabric of space itself. The engineering required to achieve this is so far beyond our understanding it borders on magic, demanding a control over reality that would make us masters of the quantum realm. Each of these cosmic power sources presents a ladder of technological advancement, each rung representing a leap in energy mastery that redefines what is possible. The path to speaking the language of gravity is, first and foremost, a path to harnessing the fundamental fires of creation. This vessel would look nothing like the rockets and shuttles of our past. Forget fiery engines and gigantic fuel tanks. A ship built for graviton wave travel would be a serene and almost featureless structure, a geometric form designed for one purpose: to shape the universe around it. At its heart, you would likely find a massive ring or a perfect sphere, a structure humming with energies we cannot see. This is not an engine for propulsion, but a field generator, a device whose sole job is to create and maintain the warp bubble. The entire outer surface of this ring might be composed of a material we cannot yet conceive, a lattice designed to focus a coherent beam of gravitons, orchestrating the compression of spacetime ahead and the expansion behind. The ship itself would be suspended at the exact center of this generated bubble, in a pocket of perfectly normal, stable spacetime. This is the safest place in the entire universe during the journey, completely isolated from the titanic forces warping reality just outside the hull. Here, the crew would live and work in an environment of calm artificial gravity, watching the stars not as points of light, but as streaks and distortions in the fabric of the cosmos. There would be no windows in the traditional sense, as the light from outside would be hopelessly scrambled. Instead, view screens would reconstruct the view, translating the complex gravitational data into a navigable image. The silence would be profound, with no roar of engines, only the faint, almost musical hum of the field generator maintaining its impossible balance. This ship is not a bullet fired into the void. It is a carefully held stitch in the tapestry of spacetime, moving because the tapestry itself is being pulled. That serene journey inside a warp bubble carries a hidden, terrifying price. The very mechanism that allows a ship to surf spacetime could transform it into a weapon of cosmic destruction. As the vessel moves, its warp bubble does not just push space aside, it sweeps up every particle in its path. Over a long journey, this bubble would accumulate a vast cloud of interstellar hydrogen and high-energy cosmic rays, trapping them within the distorted spacetime field. The ship would be gathering a storm. Upon arrival, when the warp field is collapsed to bring the ship to a stop, all that accumulated energy would be released in a single, catastrophic instant. The resulting blast of radiation and particles would be directed forward, sterilizing everything in its path. Your graceful arrival could inadvertently wipe out all life in the destination solar system, turning a new Eden into a scorched wasteland before you even took a single step outside. This is not merely an engineering problem, it is the ultimate ethical dilemma. Do you have the right to visit another world if your hello is a gamma-ray burst? And the dangers reach even deeper into the fabric of reality. The energies required to sustain a warp bubble are so immense that a miscalculation, a flicker in the containment field, could cause a catastrophic failure. Instead of gently compressing spacetime, the field could collapse in on itself, concentrating that unimaginable energy into a single point. The result would be the spontaneous birth of a black hole right at your ship's location. One moment you are navigating the stars, the next you and your vessel are crushed into a singularity, potentially dragging a large portion of the surrounding space with you. The act of travel would become an act of suicide and mass destruction. These are not simple bugs to be engineered away. They are fundamental consequences of manipulating the universe's most primal force. Mastering gravity is not just about gaining power, it is about bearing the responsibility for forces that can create and erase worlds. The language of spacetime is beautiful, but a single mispronounced word could shatter a star. That signal arrives not as a crackle of static, but as a perfect rhythmic pulse in the fabric of space-time. We have our proof, a message from the stars. But the message itself is a locked box, and we have lost the key. The first challenge is not linguistic but physical. Our computers receive the signal as a stream of raw data, a sequence of precise gravitational fluctuations. The wave's amplitude and frequency are changing in a complex, non-repeating pattern that defies any known natural source. It is a river of ones and zeros written directly into the geometry of the universe. But we have no idea how to group those digits. Is a single pulse a letter, or is a sequence of 10 pulses a word? Is there a header, a piece of metadata that tells us the length of the message or the size of its data packets? We are staring at a cosmic Rosetta Stone, a slab of granite covered in beautiful, inscrutable hieroglyphs, but without the accompanying Greek translation that allowed us to crack the original code. Our only hope lies in finding a universal language, a set of concepts so fundamental that any technological species would understand them. Mathematics is our first and best candidate. We would search the signal for the simplest, most elegant truths. We would look for the sequence of prime numbers 2, 3, 5, 7, 11, a pattern that cannot occur by chance in a signal of this complexity. Finding it would be our first breakthrough, confirming that the message is not just ordered but numerical. Next, we might search for the ratios of fundamental constants. The value of pi, the ratio of a circle's circumference to its diameter, is the same everywhere in the universe. A hydrogen atom vibrates at the same frequency in a galaxy a billion light-years away as it does here on Earth. If the message contains these universal numbers, it gives us anchor points, a shared vocabulary of reality upon which to build a translation. But numbers alone cannot convey meaning. The true breakthrough would come from a transmission that pairs a mathematical concept with a simple, visual representation. Imagine a section of the signal that first sends the prime numbers, then sends a bitmap, a grid of ones and zeros that, when arranged correctly, forms a simple geometric shape like a circle or a triangle. This pairing of abstract number with concrete form would be the Rosetta Stone's Greek text. It would demonstrate that the sender understands we need to learn their symbolic language from the ground up. They would be teaching us, starting with nouns for the most basic shapes and forces. A following transmission might pair the mathematical constant for gravity with an animated sequence showing two objects orbiting each other, a gravitational dance. This would build a dictionary, one entry at a time. The ultimate goal would be to move beyond physics and mathematics into the realm of ideas. How do you communicate concepts like consciousness, friendship, or fear using only math and pictures? This is the final and perhaps insurmountable wall. The message in the Graviton wave might remain forever partially decoded, a beautiful poem from the stars whose deepest stanzas we can never truly understand. The silence of our detectors does not mean nothing is happening. Right now, in laboratories buried deep underground and in particle colliders of staggering scale, scientists are conducting experiments that inch us closer to that first cosmic whisper. These are not telescopes pointed at the stars, but Chinese letter instruments probing the very laws that hold the universe together. At the Large Hadron Collider, physicists are not looking for gravitons directly. That would be like trying to spot a single specific grain of sand on an entire beach during a hurricane. Instead, they are searching for their ghostly signature in the debris of unimaginably powerful particle collisions. When protons are smashed together at nearly the speed of light, the energy released can, for a fleeting instant, condense into new forms of matter. The hope is that within this chaotic aftermath, we might find a telltale imbalance, a missing piece of energy and momentum that could only have been carried away by an invisible, weakly interacting particle. Spotting a graviton this way is a monumental long shot, but it represents a fundamental shift in our approach. We are no longer waiting for the universe to speak. We are trying to force it to reveal its secrets under the intense pressure of our own machines. Meanwhile, a quieter revolution is unfolding in the realm of quantum physics. Experiments are now attempting to measure gravity's effect on the smallest possible objects. Imagine a tiny, mirrored bead levitated in a vacuum by lasers and cooled to near absolute zero. At this scale, the bead behaves as both a particle and a wave, its quantum nature laid bare. The profound question is, how does gravity, the force that shapes galaxies, act on this single, tiny quantum object? Does it cause its wave function to collapse? By observing this interaction, we are testing the boundary where Einstein's smooth spacetime meets the fuzzy, probabilistic world of the quantum. It is an experiment that probes the very foundations of how these two pillars of physics might one day unite. The most ambitious projects aim to go beyond mere detection and create gravity itself. Teams are exploring ways to generate synthetic gravitational fields in the lab. One theoretical method involves using intensely rotating superconductors. These are materials that, when cooled, can carry an electrical current forever without losing energy. The theory suggests that if you spin a superconductor fast enough, it might create a minuscule artificial gravitational field, a faint echo of the warping produced by a planet. We are not talking about a force you could feel, but a distortion so tiny it would require instruments of incredible sensitivity to measure. Success would be a watershed moment, proving that gravity is not just a force we observe, but one we can engineer. These are the first clumsy words in a language we are desperate to learn, spoken not into the void, but within the quiet confines of our own laboratories. The galaxy slowly opens its doors, not with a roar of rockets, but with the silent, graceful pulse of engineered spacetime. We are no longer prisoners of distance, confined to our tiny, pale blue dot. This is the dawn of the Graviton age, a future where humanity's footprint is no longer measured in miles, but in light years. Instant communication via Graviton waves weaves our scattered colonies into a single, conscious network. A question posed on a world orbiting Proxima Centauri is heard and answered on Earth in the same moment, the lag of years replaced by the immediacy of a shared present. The tyranny of the rocket equation is a forgotten lesson from a primitive past. Starships, no longer clumsy vessels of fuel and fire, are architects of geometry. They slip into custom-tailored warp bubbles, their journeys not a struggle against the void, but a serene negotiation with the fabric of the cosmos itself. A family could have breakfast in orbit around Mars and decide to visit the crystalline shores of a world in the Gliese system for dinner, the journey itself a peaceful interlude inside a pocket of stable reality. Our relationship with the universe becomes intimate. We no longer just look at the stars, we converse with them. The subtle gravitational hum of a neutron star becomes a data stream we can interpret, its spin and composition as readable as a morning news report. The mysterious dark matter halo of our galaxy is no longer an invisible ghost, but a tangible medium, a substrate through which our clearest, most important communications travel. We learn to listen to the background chorus of the cosmos, and we learn to add our own voice to the song. This mastery over gravity fundamentally alters our sense of self. We are no longer fragile organisms clinging to a single rock, but active participants in a galactic community. The great silence of the Fermi paradox is broken, not by a single message, but by our newfound ability to hear the constant, bustling conversation that was always there. We find that we are not alone and that we never were. We were merely deaf. In this new chapter, the human story expands from a planetary biography to a galactic epic. We become the engineers of reality, our destiny intertwined with the very threads of space-time. The universe is no longer a place we visit, it is a place we help to shape. From a ghostly particle to a voice that could cross the galaxy, this journey through Graviton waves charts a course across the furthest frontiers of human thought. We began with a faint pulse from a dead star, a ripple in spacetime that led us to the quantum phantom, the Graviton. We saw how its immense power, seen in the collision of black holes, might one day be harnessed and shaped. This path winds from the theoretical warp drive, a ship surfing the fabric of reality, to the ultimate communication channel, a signal that passes cleanly through stars and dust. It forces us to confront the Fermi paradox with a humbling possibility that the universe is not silent, but we have been listening with the wrong ears. Every piece of this puzzle, from the energy of a Dyson sphere to the ethical peril of our arrival, is still theoretical, a blueprint written in the language of mathematics and hope. Yet it stands as one of the most thrilling horizons in all of science, a promise that the force which holds our feet to the ground could one day carry us to the stars. The next time you look up at the night sky, remember that the darkness between those points of light is not an empty void. It is a medium, a canvas, a potential network waiting for a connection. Our story as a species may just be beginning its first, tentative chapter in a much larger book. Stay curious, keep looking up, and listen for the whispers written in gravity itself.